This is the second of the two videos on electromagnetic radiation and energy. This one is on EMR and energy. First, a quick review of the previous video. Lambda is equal to the wavelength, the distance from crest to crest of any wave, and the unit we use is the meter, but you can use any of the prefixes in front of the meter. Nu is the frequency. Frequency is how often a wave passes by a reference point in 1 second, and the units are per second, second to the minus 1, or hertz. They're all equal. C is equal to the speed of an EMR wave. You're used to thinking that as the speed of light, and the value for this, which is a measured value, 3.00 times 10 to the 8th meters per second, and because it's measured it has 3 significant figures. And C is equal to lambda nu. Speed equals wavelength times frequency. Now, you need to know that electromagnetic radiation can act as either a wave or a particle. This is called wave-particle duality. This is part of quantum mechanics. And though we're going to use the particle for this part, we will interchange wave and particle. And as Forrest Gump says, that's all I'm going to say about that. A particle of light is called a photon, and a beam of light is made up of almost an inconceivable number of photons. Each specific frequency of EMR, or each specific type of photon of EMR, is associated with a very specific energy. What does that mean? It means that the photons of anything glowing red have the same energy. Anything that is yellow hot, the photons have the same amount of energy. This explains why red lasers have less energy than green lasers, which have less energy than violet lasers. Which then means that you can ask the question, why? The answer is E equals h nu, which now allows you to say, and what does that mean? Okay, let's run through the terms. E is the amount of energy for one photon, and that unit is given in joules, which is symbolized by a J. This is a metric term, so you can use all of the prefixes here. H is called Planck's constant. It's equal to 6.63 times 10 to the minus 34th joules times second. A really, really small number, and also a number you do not have to memorize. You'll be supplied with this. Nu is the frequency in the usual units. So h nu equals the energy for one photon. It will be a really small number. But as any beam of light has gazillions of photons, light beams, or EMR, can have a lot of energy. So E and nu are directly related. The energy and the frequency are directly related. If one value goes up, the other must go up. So therefore, each level of energy must have a very specific frequency. Now, we also know that nu times lambda equals C, and therefore each frequency has a very specific wavelength. So, if each amount of energy is associated with a specific frequency, and any frequency is associated with a specific wavelength, then each amount of energy is associated with a specific wavelength of EMR. The higher the frequency, the higher the energy of the EMR wave. The higher the frequency, the smaller the wavelength. Therefore, the smaller the wavelength of EMR, the higher the energy. And here is the picture of the spectrum of EMR again. Notice frequency increases from right to left, wavelength decreases from right to left, but energy increases from right to left. So increasing the frequency increases the energy, decreasing the wavelength increases the energy. So how are we going to use this? Example 1. How much energy is in one photon of light, which has a frequency of 5.00 times 10 to the 14th hertz? What do you know? You know that E equals h nu. You know that H equals 6.63 times 10 to the minus 34th joules times seconds. You know that the frequency is 5.00 times 10 to the 14th per second. You know 2 out of the 3 variables in the equation, so you plug and chug. You set this equation up, do out the math. Notice the seconds cancel out, and you get 3.315 times 10 to the minus 19th joules per photon. But both the 6.63 and the 5.00 have 3 significant figures. So your final answer is 3.32 times 10 to the minus 19th joules per photon. Example 2 is for you to try. You've got a photon with an energy of 8.98 times 10 to the minus 20 joules. What is the frequency? Go. The answer is 1.35 times 10 to the 14th per second. How did we get this? What do you know? You know that energy equals h nu. You know that energy equals 8.98 times 10 to the minus 20 joules for the photon. You know that h is 6.63 times 10 to the minus 34th joules per second. You know 2 out of the 3 because you know that nu equals nu. Now you just need to plug and chug. Set the equation up. Divide both sides by 6.63 times 10 to the minus 34th joules per second. It cancels on the right, leaving you only with nu. Do the math on the left. You get this number on your calculator, but you should only have 3 significant figures, so you get this value for the final answer. One final example. You have some violet light with a wavelength of 425 nanometers. What is the energy? Go. The answer is 4.68 times 10 to the 19th joules. How did we get this? What do you know? You know E equals h nu. You know E equals E because that's what we're asking for. H is 6.63 times 10 to the minus 34th joules times second. Frequency equals frequency. We now have an equation with 2 unknown variables. We can't just plug and chug. But wait. We do know that C equals lambda nu. We know that C equals 3 times 10 to the 8th meters per second. We know that lambda is 425 nanometers, but we can convert that to 4.25 times 10 to the minus 7th meters. Frequency is still equal to frequency, but now we know 2 out of the 3 variables for this equation. So you set this equation up, solve it for nu, and you get a frequency of 7.06 times 10 to the 14th per second. Let's go back to E equals h nu. E still equals E. We still don't know that value. H, being a constant, still equals 6.63 times 10 to the minus 34th joules seconds. Nu, we now know it's 7.06 times 10 to the 14th per second. Set up the equation. Solve. This is the number you get on your calculator. And so you set it into correct significant figures and you get the 4.68 times 10 to the minus 19th joules. And now if you remember, the value for the red light was 3.32 times 10 to the minus 19th joules. The violet has more energy than the red, as we predicted. So in review, got to remember what wavelength is. You have to remember frequency. You've got to remember that frequency times wavelength is the speed of a wave. For EMR, the speed of the wave is 3 times 10 to the 8th meters per second. So you can set the equation up this way. Lambda and nu are indirectly related, but if you know one, you know the other. From this video, E equals h nu. E and nu are directly related. If one goes up, the other must go up. And E and lambda are indirectly related. If one goes up, the other must go down. As frequency increases, energy increases. As wavelength decreases, energy increases. In the next lecture, we're now going to tie what you know about light and energy, or EMR and energy, and what you know about orbitals to come up with what is called the emission spectrum of elements.